Let's start. So last time we skipped some of the part in the lecture week 1. So let me explain some of the important material that we skipped last time. So as an example of solution of a spring motion, so we have a spring motion equation. So we have this differential equation, right? And we claim that this function is a solution function of the differential equation that we previously shown. So in order to check that this is a solution, we have to take a derivative of this function. So the problem is we have zeta and omega as real numbers, but here this could be imaginary number. So we know how to take a derivative of exponential function with real coefficient, but we don't know how to take a derivative with complex coefficient. So let's take the Euler formula again. So we have Euler formula. Now let's think about how to take a derivative in terms of x of e to the ix. Here I is pure imaginary number. So what happens is if we take a derivative of cosine and sine, 잠깐만요. So there's some lag here. Okay. I think there is a 10-minute lag. 프로그램 문제 같은데? 된 거 같은데 잠깐만요. 아이고. 자 이제 또 들리죠?
안 돼. 아, 됐다. 말해봐봐.
자 이제 들리나요? 네. 네. 근데 생각에 이거 모니터를
돌아가고 있어 아직.
모니터를 뒤집으면은 이거를 지금 렉이 생기는 것 같아. 최대한 안 뒤집고 써야겠는데. Okay, let's begin. So we're going to take a derivative of e to the ix in terms of x. So what happens is we get minus sine x plus I cosine x. So this is equal to I times cosine x plus I sine x. So basically this is equal to I e to the ix. So when you take a derivative of exponential function, you can just consider this I as a real coefficient, although it's not real coefficient, but consider this as if it's just the real constant, and then take a usual derivative in the derivative of exponential function. So you get I, a coefficient of x, comes out of this exponential. So you get this result. So for example, if you have e to the x plus e to the x plus I omega t, where omega is now real coefficient, then you can take a derivative in terms of t. Suppose that we have x also as a function of t. So this is also a function of t. then you can take a derivative of product of e to the xt times e to the I omega t. So you can take a derivative of first part x prime t, e to the xt, and e to the I omega t, and then take derivative of the second part, which is I omega e to the I omega t. So that's the result of derivative of complex coefficient, complex power of exponential. So when you check that this is a solution of the spring motion differential equation, you can consider this whole thing as a coefficient, regardless of whether this is imaginary number or real number. Just take t as the variable that you're taking a derivative with, and this is a real coefficient. If you have any question, please ask right away. And electric circuit. So you can look at the picture in the file that I uploaded in the LMS site. So let me explain how to set up the differential equation of electric circuit. So we start from here. Let me draw a brief picture of circuit here. So we start. We start from here. So this is a voltage. Usually this represents DC instead of AC. So sometimes instead of this notation, sometimes people write E, right, like this one. And here we have a resistance, and here we have capacity, and here we have coil. Now the electron circulate from this side of the voltage and then to this direction, and when the electron cross over the resistance, we consider that the voltage drops by R times the current IT. So we're measuring how much voltage drops whenever it crosses this component of electric circuit. So when the current passes through the resistance with coefficient R, or resistance constant R, the unit is ohm, the voltage drops by R times I. R is constant, so this is the function in terms of t. And then I think the order is a little bit different. So when the current actually cannot pass through the capacitor, because capacitor only accumulates these electrons. However, when capacitor has enough electrons stored coming from the voltage, then it generates its own voltage. So we can consider that the voltage generated by capacitor is the voltage generated in the reversed way of voltage generated separately from the actual source of voltage in the reversed way. So suppose that we have the amount of charge that's stored in the capacitor as the integration of the current IT from 0 time to time t. So this is the total charge stored in the capacitor. So when capacitor has QT charge, then it generates the voltage by this amount of charge divided by C, where C is the capacitor constant. So the unit is farad. So let me write the equation here. So we started from the voltage, total voltage ET, and when it crosses over the resistance, its voltage drops by R times IT, and when it crosses actually it's not crossing over, but it's when we measure the voltage, when we pass the component capacitor, then the voltage drops by the total charge accumulated on the capacitor divided by the constant C. And then the last one is the inductance, the coil. And because of this coil, there is a magnetic field generated, so it kind of makes it hard to electron to cross over the circuit. So you can also think about this is something like the resistance, so that it drops the voltage. So how much the voltage drops is measured by the derivative of I, the rate of change of current, times the L, where the L is the constant, inductance constant, whose unit is henries. So minus L times di dt. So now the electron comes back to the original source of voltage. So the voltage has to be equalized. So the whole thing adds up to 0. So now we have derivative and integration sign together in one equation. We want to make it as a differential equation. So we take the derivative on left and right hand side. So we have a prime t minus r I prime t, and then by the fundamental theorem of calculus, when you take a derivative here, we have 1 over c times it and minus l times I double prime t. So when you move all the part whose signs are negative to the right hand side, you get second order derivative, a second order differential equation, ordinary differential equation. And this is actually linear. And if et is not constant, then this e prime t term survives. So depending on whether the voltage is AC or DC, if the voltage is AC, then E prime t survives as a periodic function, so we get non-homogeneous equation. And if we have a DC, then ET is constant, so we have 0 E prime t, so we get homogeneous equation. So we are going to solve this equation later, and I want to emphasize that this form of differential equation is exactly same form as we saw in the previous example of spring motion here, or this one. Okay. So basically, if you are able to solve second order differential equation, then you can solve the spring motion and electric circuit. Is there any questions? Okay. So the next one is epidemic model. This is an example of system of differential equations. So it consists of two or more differential equations, and each equation consists of several functions in terms of t. So for example, I think this is the best time that you can understand this differential equation, because we have we have a situation almost exactly equal to this model, and the data is updating every day. So I think this could be a good project if you want to predict what could happen after a month or two. So let me explain what this is. So in an epidemic, like spreading of disease, you can model the number of people affected by this disease. So susceptible means that this is the people who is not infected yet but capable of infected. And infected means that they already infected the disease. And removed means that either this person is cured and immune to the disease because of this antibacterial protection of the body, or they are diseased, means they died out. Okay. So we are going to model this number of people by function S and I and R. So S for susceptible, I for infected, and R for removed. So you also can divide this removed person into two groups. One for deceased, meaning died out, and one for cured and immune. And also, this also you can model a different situation, like not all cured people have immune to this virus. For example, this coronavirus has a special character that even the people who cured from this virus can also capable of being affected and infected again. So you can think about you can model this equation so that even the cured people can be either being a susceptible people or immune people. Let me explain more. So the simplest model is SI model, that people are either susceptible or infected. So there's no way to cure from the infected state. So we explained how this modeled. So this consists of two differential equations with the same coefficient alpha, and susceptible people only decreases and infected people only increases, and the ratio, the rate of increased and decreased of susceptible and infected and susceptible are the same. And it's also it's proportional to the number of susceptible and infected in the same time, because it requires in order to spread the disease, you have to interact with susceptible people and infected people. So it depends on the product of the number of people of two groups. So the little bit more complicated model is the SIS model, which means that infected people can also be also can cured or recovered, but they're being susceptible again. So there's no way that they can immune to this disease. So everything is same except there's one more term on each equation, that susceptible people increases by the ratio is proportional constant is B with proportional to the number of infected. So there is a portion of people in the infected group that they can be cured, but they are become susceptible again. They can be infected again to the disease or virus. And the same number of people, same amount of people who cured from the infected state will decrease the number of people in the infected group. So exactly same amount of people, same amount of ratio of change is decreased from these infected people. And then there's a mixed state. It's not exactly a generalization of the second one. The third one is that if every infected person ends up being dead or immune to the disease, then we have this SIR model. This is called SIR model. And this is most standard model for modeling the epidemic. So we have susceptible only decreasing, and we have infected increased from the susceptible people, and also there is a decrease rate by proportional to the infected number of infected people, and this is by cured or dead. I don't like the word dead, but okay. The more better word is deceased. Okay. Anyway, so we have two components that affects the change of the infected people. So one is from the susceptible people, and the other is from curing the infected people. So what happens when the people are cured from infected state? They goes to the removed state. So why we taking the dead people or immune people in the same group? Because they are now in the state of this virus effect. Because if they are dead, then there's no way they can be infected or cured anymore, because they're not exist anymore. And if it's immune, then they also have not effect on the virus effect. So if the situation is getting stabilized, then you can expect that everyone should be, so susceptible people start from total population, say 1,000, and later it has to be goes to zero at some point, because everyone's are susceptible in the beginning, right? And then this epidemic ends when everyone has to be infected at once, and the number of infected people start from zero and going from zero to somehow 1,000 at some point, right? Not 1,000, sorry. So because at the same time they are removed, cured or being dead. And then what happens to removed? So it's also start from zero, but later, if the situation is stabilized, means the virus is disappeared or disease also disappeared, then this removed state has to be start from 0 to 1,000, because everyone has to be either cured or immune to or dead. And what happens to the infected people? So in the middle they have increased a little bit, but later it has to be goes to zero for infected people. So that's the situation when this epidemic is stabilized. But if it's not stabilized, then you can consider that the infected people eventually goes up to 1,000, the total population, and there should be if you divide your removed group into two groups, two subgroups, like people who deceased and people who immune, then deceased people have to be go up to the total population. That's the total extinction, right? Total extinct of the population. So if that happens to human population, that's very tragic situation. But you can also apply this situation to the animal population or bacterial situation. So there are many situations that you can apply this thing. So that's the part that we skipped last time. So if there are any questions, okay. So please ask any questions. In SIS model, deceased people not taken into account. So question is, in SIS model, we don't take account of deceased people. So if the infection is not severe, then we can consider that nobody dies because of this disease. It only matters of how much people are suffer from disease. So in SIS model, we don't consider how much people are dead or immune. It only matter of the balance between infected people and susceptible people. But so as I said, this second one and third one are not exactly. So third one is not a generalization, just different situation. But you can combine these two situations. Say some people are, so in this case, you can put one more term, say C, so that some of the infected people goes to susceptible ones, and some of people goes to the removed ones. So you can put one more terms on the second and first and second equation. Then this is a generalization of the second situation. You can also split these two. So say B1, I1. So here we I1, and then minus B2. Sorry, so just I. Sorry, so B2, I, and then you can split these two equations. So B1 for R1 and dR2 dt. So there's a four differential equation in this case. B2 I2, B2 I2. So that now, I'm sorry, R1. So R1 is number of deceased. Sorry, and R2 is number of immune. Then you can set up, if you set this equation like this one, then you can control the situation more accurately. How much are deceased, how much are immune. Does this answer your question? Okay. Okay, let's move on to the second week. So second week is somewhat familiar material, so I'm not going to give detailed examples. Instead, I'm going to explain how I understand important theorems on calculus and how you have to consider these equations or the properties of calculus in order to understand the differential equations. So let's start from the definition of continuity. So let y equals to fx be a function defined on interval I. So this is the math symbol I, containing a. So a is the point, a is the value in this interval. If fx gets arbitrarily close to the point a, I'm sorry, so I think there's a typo here. If fx gets arbitrarily close to a, okay, so here you have to put a comma here. Value L, I'm sorry, sorry, this I made a mistake. So this is not a symbol a. Close to a value L as x approaches to a. Yeah, so this is a symbol, math symbol a. Let me circle the symbols. I'll try to distinguish these symbols, the letter A and the math symbol A, from the both side. Then we say that L is the limit of fx at A, so A is a symbol, and we denote this as the limit of fx as x goes to a is equal to L. So this is the usual definition that you already know. So we have a function, the graph of function looks like this, and we have a point A in x-axis. As we approach A from left and right hand side, if the value of function approach to the value A, then we say fx has a limit L at A. And this is an intuitive definition of limit and continuity. We can define this continuity rigorously using epsilon delta. Okay. 계속 끊기나요? 지금도? 지금은 괜찮을 텐데. 제가 보면서 하고 있거든요. 네. 이게 중간중간에 갑자기 핑이 확 떨어질 때 끊기는 것 같은데, 자, 이 부분만 한글로 다시 얘기를 할게요. 빠르게. 지금 우리가 그러니까 fx가 연속이다, a에서 연속이다라는 정의를 얘기를 하고 있어요. 여러분들 다 아시는 정의예요. x가 a로 왼쪽이나 오른쪽으로 가까이 갈 때 이 함수 f의 값이 l로 가까이 가면은 우리가 함수가 이제 l로, 그러니까 함수 fx의 극한이 l이다 이렇게 얘기를 하죠. 사실 이거는 컨티뉴이티에 대한 정의는 아니에요. 그냥 이거는 리밋이 얼마다라는 얘기예요. 만약에 이 L이 FA가 되면은 이제 A에서 연속이다 얘기를 하죠. 근데 이제 연속의 정의는 거기에 이 L이라는 값이 함수 값이랑 같을 때 얘기를 하는 거고, 이거보다 이제 더 엄밀하게 이제 정의하는 방법이 있는데, 참. 핑은 괜찮은데? 이게 핑이 왔다 갔다 하네요, 좀. 잠깐만요. 제가 지금 요거 인터넷을 좀 바꿔볼게요. 죄송합니다. 자, 그래서 좀 이제 엄밀하게 정의하는 방법이 있는데, 이거는 건들진 않을게요. 근데 이제 관심 있으신 분은 한번 읽어보세요. 이 부분은 굳이 여러분들이 수학과 안 갈 거면은 굳이 몰라도 상관은 없어요. 아무 상관 없어요, 진짜로. Okay, so remarks. There are a few important facts about the limit. So we're only talking about the limit here. Continuity is when you apply the value of the limit into the value of function. So existence of limit of a function at A, so A is a symbol, does not imply the existence of FA. So having a limit at some point does not mean that we have a function defined at that point. So conversely, if the function does not need to be the function does not need to be defined at A for the limit to be exist at A. A is a symbol. So limit and the value of a function has no correlation. So you can have a limit even if you don't have a value defined at the point for the function, and also the function doesn't have to be defined at the point in order to have a limit. And also you can define a right limit and left limit. This is called the 좌극한, 우극한 in calculus. You learned in the high school. And the limit exists if and only if the right and left limit both exist and the same, coincide. So the third one, you can also define the limit of function when x diverges. So which means that if x goes to infinitely large or negative infinitely small, then if function levels out, which means that the value of function goes to some finite number L, then you can define the limit of your function as x diverges. So you can also define similarly, we have x goes to negative infinity, then fx goes to some L prime. Okay. So the last one is the notation of a limit can be applied to the limit of a sequence. So instead of x as a real number, and we consider x continuously moves to some point or infinity, but you can also define your variable n as an integer, so you can consider this integer goes to infinity. So from 1, 2, 3, 4, discrete way. So in this case, you can consider this sequence of numbers. So sequence means that you have an index for each value. You have index 1 number, which is 1 plus 1 to the 1 power, and index 2 number is 1 plus 1 over 2 to the power of 2, and so on. Then if this sequence converges to a number, then you can define the limit. And well-known constant is the natural constant E, defined this way. And you can also define your function in this way too. So if a function in terms of x is defined as a limit of sequence having this term x, then you can define, and if this sequence always converges to a value, then you can define your function. So in the recitation session, we're going to actually calculate how this natural number e calculated by taking lots of sequence. Okay, so definition. This is a definition of continuity. So function fx is called continuous at a in the interval I if the limit is the value of function. So here's a good example of continuity. Let's say we have a function fx which is given by x times sine 1 over x. Now it has a limit. We have a limit at x equals to 0, but this is not continuous at x equals to 0. So we're going to draw this function in the recitation session too. So how this graph looks like, this looks like this. So we have asymptotic line, which is y equals to x, and this is x, and this is y. This has a limit. If x approaches to 0, the function approaches to 0. So the limit is 0, but this is not continuous. Why this is not continuous? So I think you know the answer here. So this is not continuous because function is not defined at 0. Y is not defined at 0 because we have denominator x and you cannot plug in 0 in denominator of any fraction. So f0 is not defined. So we simply have no value to compare with the limit. So this is not continuous. So how do you make it continuous? Because you can make this function as continuous function. Just simply define your value of fx as 0 when x equals to 0. So when x is not 0, this is 1 over x, and then 0 when x is 0. Then it's continuous. And also this is another example of non-continuous function, and this is also a standard example in mathematics or analysis, but right now we don't need that. So let me define differentiability and differential of function. So if function is defined on interval I, and suppose that fx is continuous at a, the function is said to be differentiable at a if the limit called the differential, so the value of limit is called the differential of function at a, exists. And how does it defined? It is defined as a limit of ratio of difference of f and difference in x around a. So I think you all know this definition already. Now, here's a good example. So we defined fx equals 0 when x equals 0 in the previous example in order to make this function continuous. Now, we want to ask whether this function is differentiable at 0. So, in the definition, you have to have a value at the point where you're going to check the differentiability of a function. So f0 has to be defined. But now we already defined the f0, so you can try to compute the limit here, f0. And then this becomes limit of x0 and now f0 is 0, so we get fx, and fx, let me write fx here, fx. Now, when you take a limit, this is, I think you all trained that this fx is not equals to the value when x is equal to 0, because x is approaching to 0, not equals to 0. So you have to plug in this formula, not 0 here. So we have limit of x sine 1 over x, x. Now, x is not 0, so this is a small number close to 0, so still you can cancel out these two. And what you have is the limit of sine 1 over x. And sine 1 over x looks like this. So as x goes to 0, 1 over x goes to infinitely large or infinitely small, depending on whether x approaches from the right or left of 0. So whichever happens, when x goes to 0, this sine 1 over x goes to 1 over x goes to infinitely large, and sine x oscillating from 0 to 1, and the number of times that the sine function oscillates are infinite as x goes to infinite. So this infinite number of oscillation happens in the small interval from 0 to some small number. So you have an infinite number of oscillations. So basically you cannot draw this function at 0. And you cannot determine whether this function approaches to some finite value. You cannot expect that this goes to 0, because at the point near 0, there are all range of value of function from -1 to 1. So there's simply no limit. So you cannot take a limit here. So this does not exist. So this concludes that this function is not differentiable. However, there is a function looks similar to the previous example, but still differentiable. So here we have x squared instead of x. Now, if you simply take the definition, then what happens is x squared sine 1 over x, and x cancels out. We have limit of x sine 1 over x as x goes to 0. So we saw this function has a limit 0. So this is equals to 0. So what happens is this function looks like this. We're going to draw this in the recitation session. So there is a asymptotic line. Looks like y equals x squared. So instead of the asymptotic lines look like a linear function, now we have a quadratic function approach to 0. So the graph of function looks more flattened at 0. And in this case, we have a differentiability of function because of the definition, and also if you're looking at the graph. Differentiability in your intuitive definition is the slope of a function. So when you try to compute the slope of a function of previous example, the slope changes from -1 to 1 or to the infinity because you have too much oscillation in the small interval near 0. But in here, you can intuitively think that this graph is flattened out along this y goes to x squared graph in a quadratic way. So we have a slope getting flattened and flattened and eventually becomes 0 when x goes to 0. So this is two very different example of the differentiable and non-differentiable functions. So I want to emphasize that if you want if you like the rigorous definition, you can just follow the epsilon delta or this definition. But I think it's more important to really understand what's the meaning, what's the feeling of differentiability. So I think this first and second example explain this definition of differentiability best, because there are very different feelings of these differentiable functions and non-differentiable functions. They are both continuous functions, so you know how continuity is defined intuitively, but differentiability is somehow you always know that you always consider the differentiable functions in your problems. So if you want to consider what's not differentiable and what is differentiable, just compare these two examples, and you will you have to intuitively know how this differentiable function look like at the point. Okay, let's move on. So we have a function may not be differential. So this is a small remark that somehow we learned in high school that the differentiability means that you have a slope, which means that you have a tangent line. Tangent line means that the line is slightly touching this graph of a function. Now, but having a tangent line does not mean that this function is differentiable. For example, we have a fx equals to x to the 1 over third. So we have a graph looks like this. So we have a vertical slope. Still, this function has a tangent line at x equals to 0. So simply, tangent line is a line in a 2D, two-dimensional plane which is tangent to this graph. This tangent graph happens to be a vertical line. It still is a tangent line, but it's not differentiable. You can check by definition or simply because slope is infinite. You don't have a differential at equals to 0. So having a tangent line does not mean that this is differentiable. And for the English notation, we have a derivative, word derivative, represent for the function, which maps each value x in the interval of domain to the differential of a function at that point. So this function is called the derivative. So the difference between derivative and differential is that differential is a value of differentiation, and which means the just value of a limit defining the differentiability of function, and derivative is a function defined on the interval of a function where it's differentiable, which maps each point in that interval to differential. Okay, so this is differential and this is derivative. And this is a well-known formula of differentiation. So product formula and fractions, derivative of fraction and derivative of composite of functions. And this is a side note that if you have a derivative which is also continuous on the same domain of f prime, then we say f is continuously differentiable. So if you don't have a continuously word here, just f is differentiable, it means that f prime exists. And also it means just f prime, the derivative is a function. You can define a derivative. But if you have continuously differentiable, then this f prime is continuous. And you can also say that this is a C1 function. So in C0 function is simply continuous function. Continuous function. C1 means its derivative is continuous. And what does C2 means? If we say f is C2 functions, then the derivative of derivative is continuous function. Right? Okay. And you can define inductively that function is Cn function if the nth order derivative is continuous. Okay. So basically, if you want to solve second order differential equation, then you have to have a function. You're finding a function which is C2. So the differential equation contains second order derivative of function, and this equation is defined continuously on value of x. So you have to have a second order derivative function as a continuous function. So automatically you're finding a function whose second order derivative is continuous. So this is very important later if you want to find the general solution, and also if you want to distinguish the special solution from derived from general solution and singular solution. Sometimes singular solution does not satisfy C2 even if you're solving the second order derivative at the differential equation. So when we say we solve the differential equation, we are only finding a solution with this property that the function second order derivative is continuous. There could be other functions which does not satisfy C2 conditions. So later we were going to see that. Now we have a formula. Well, this is it's not a critical formula that you have to understand right now, but you can derive if you know how to take inductive method in proof. So we have fg prime equals to f prime g fg prime, and what happens to fg double prime? So this is taking another derivative of this sum. So we have f double prime g plus f prime g prime plus f prime g prime plus fg double prime. So we have f double prime g 2 times f prime g prime and fg double prime. So we have coefficient from 1, 2, 1. Here 1, 1. So this is like a binomial expansion. We have 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and so on. So this is for so first order, and this is second order and third order, fourth order. So when you take when you increase the order of derivative, you have sum of these products of the derivative of each functions with coefficient following the exactly same coefficient from Pascal triangle. And so this one is usual in your usual notation is n choose k. Okay. Okay. Any questions? No questions? Okay. Okay, so inverse function. Let f be a function defined on interval I to interval j. So range. So this is called the codomain, and this is called the domain. So this is codomain, and this is domain. So what is range? This is a subset of a codomain defined by the set of all values of functions for each point in the domain. So this is subset. So codomain could be the same set of range, but usually the range is smaller set of codomain. We say f is one-to-one correspondence if for each y in the range, this is range R, there is a unique element x in the interval such that y is equals to fx. So we have a well-known diagram. We have R and I. So if you pick any point in the range, you have to have exactly one point x which maps x to y. So in that case, you can take an inverse function from R to I, so that if you composite two functions, you get the identity function. So this is not D, so this is I. Okay. So every one-to-one correspondence has its inverse function. It's obvious. So exponential function is one-to-one correspondence. So for example, you have to have a range which is positive integer, not equals to 0. So if you just e to the x defined on entire real to positive real, then you can take an inverse map from positive real to the entire real, and that's defined as logarithm. Okay. An exponential and logarithm function is the basic block of defining another functions. For example, if you want to define exponential function whose base is not e but some other value a, then a to the x function is defined as the composite of two functions, which is e to the x times log a, which means just e to the log a coefficient x. Okay, so this is perfectly logistic definition. And also you can define a power function with a power not equal to integer. A can be any real number. In this case, you can take a composite of exponential and logarithm, just interchanging the role of a and x. We have a times log x, just as in this expression. Okay. So no questions? Still no questions? So please either memorize or understand this formula. This is very important formula. So if you want to take a derivative of an inverse function, you can simply take the reciprocal of the function, derivative of function. So how do you derive this equation? So importantly, you have just note that I used y and x, who's related by y equals to fx. So in usual definition of the inverse function derivative, it writes as this, prime x. Okay. So think about f inverse of fx equals to x. Okay. So how do you, if you take a derivative on left and right hand side, first, this is a composite of two functions, f inverse function, f function. So you have to take a derivative of outside function, which is f inverse, and you take the outside function, and then you take the derivative of inside function, f prime x. And then you get 1 on the right hand side, taking derivative of x. And just taking this f prime x to the right hand side, you get you get this expression. And then I just replaced fx as y because this is more convenient. Now think about this function, sine inverse x. Basically, entire sine has no inverse because this is a one-to-one correspondence. But if you restrict your domain from minus 1 over pi over 2 to pi over 2, you can take an inverse because now it's one-to-one. So when we consider the inverse function of sine, we are taking a minus pi over 2 to pi over 2 domain of sine. So the range, this becomes the range of inverse of sine. So the derivative looks like this. So how do you take this derivative? The easy way is just simply consider sine inverse x equals to y, which means that x is equals to sine y. And then instead of taking dy dx, so that's the derivative of inverse sine, let's take dx dy. It's dx dy. Then you get cosine y, right? Because we are taking y as an independent variable and x is a dependent variable. And then cosine y can be expressed as a square root of minus sine square y, and this is equals to 1 over square root of 1 minus x squared. So now usually we need to take a plus minus sign here, but we only have a minus sign because cosine y is always positive because we restrict our domain from minus pi over 2 to pi over 2. And then let's flip this. So we want to, in the beginning, we want to find dy dx, and this is equals to the reciprocal of the dx dy. So we have 1 over square root of 1 minus x squared. And that's it. And there's another definition of sine, hyperbolic sine, hyperbolic cosine, and you can also define your inverse of hyperbolic cosine. So hyperbolic cosine looks like, so when x goes to 0, it's 0, so this looks like this. So this has an inverse function for entire domain. So you can define your inverse hyperbolic sine for entire range of sine, hyperbolic sine, and also define your derivative of hyperbolic sine and define this way. So you can use the same method, or you can also define the actual course inverse of sine, hyperbolic sine, as the logarithm. Okay. Also, this is useful fact that instead of plus, you have a minus in the square sum of hyperbolic cosine and hyperbolic sine. Okay. Okay, I think we can stop here. The rest of material can be covered in the next lecture. So before we move on to the recitation, is there any questions? No questions? Okay. Okay, so let's move to the MATLAB. Okay. So let me start from where we stopped. So we tried to plot the graph of a function the last time. I briefly explained what lean space is. So this basically is a command that generates an array of values evenly distributed from the first starting point to the end points. We're going to study about this one further. Let me explain how to define a function. So usually if you just want to calculate something, you don't need a function. But if you define function, you can make your code more concise and readable. So let me define a easy function here, or just copy paste this section here. So in order to define a function, you have a two-way of defining function. One is define your function in the script. Another way is define a function in a separate script as a function file. So for now, let's learn how to define function in the command line. Suppose that you want to define one variable function defined as log x. You can use this syntax. So f is the name of function that you're going to use, and this at symbol is defining which symbol is used for the variable of function. So the variable inside of this parenthesis are used as a independent variable of function. So now we have a one variable function, we only have one symbol. If you want to define a two variable, multivariable function, then put more variables inside this parenthesis, separated by comma. And then the last expression is the value of function for the expression for computing the value of function. Now, for example, let's say we define our natural number as e, and then we define the function. This way, And let's try to calculate f1 and fe. Okay. Run. Oh, okay, yeah. Oh, it's not running. Run. Yes. Oh, okay. Still running. So this is drawback of using MATLAB online. So sometimes it's very slow. So what you can expect is if you define after you define the function in this way, you can call your function using the parenthesis. So if you put f parenthesis 1, you're sending value 1 into the variable x, and then the output is log of that value. So this function, this value, this output, the output of this one will be 0. This should be log 1, and should be log e. So basically this should be 1. Okay, I think it's too slow. So okay. 자, 이거 다시 좀 껐다 킬게요. 저장이 안 돼 있나? 저장이 안 돼 있군. 오케이, 다시 껐다 키니까 되긴 되네요. 좀 봅시다. 잠깐만요. Okay. Okay, so let's define E as a natural constant, and F1, Fe is defined to be outputs to be 0 and 1. Okay. So if you want to define two variable function, so there should be separated by comma. Each variable, independent variable, must be separated by comma, and let's say x square plus y square. Okay, and let's call 1, 2 here. So we're basically taking 1 square plus 2 square should be 5, right? So answer 5. Now, when you define your function, you have to think whether you're going to use this function using array or simply a single value of real number. Because since I used the single value of real number to compute the value of function, there's no error message here. However, if I want to use array as an input of variable, then this makes a problem. Suppose that I have, let's say x equals to 1, 2, 3, and y also equals to, here we have 1, 2, 3 here, okay? By the way, the x and y used for the definition of g does not conflict with the x and y in the outside. So this is temporarily variable. So as even though I use the x inside of the value of defining f and defining g and also y, you see that workspace doesn't contain x and y in the variable. So this is not used in the entire script. But however, if I now define x and y as a 1 by 3 array, then after executing this, now we have an x and y, and this is not same variable used in the definition of function. And then let's say I want to take a x and y as an input variable in the multivariable function g. So obviously this makes a problem. So what's the error message? So it says incorrect dimensions for raising a matrix to power. So what this function tries to do is putting entire array into the formula of x squared and y squared. So basically what it tries to do is this 1, 2, 3 square. So this one doesn't make sense because now 1, 2, 3 is 1 by 3 matrix. You cannot multiply 1 by 3 matrix with 1 by 3 matrix. The first matrix, the number of column of the first matrix should be the same as number of row of the second matrix. So here we have 1 by 3. This is not squared. It's not even a square matrix. So this matrix multiplication does not make sense. What we are trying to do here is taking an entry-wise square of x and y and sum those two entries of the matrix. So entry-wise operation requires dot. So when I put dot in front of the power symbols here, this is not computing the function g. I'm simply computing this one. So result is 2, 8, 18 because 1 squared plus 1 squared equals to 2 and so on. So if I put dot in front of this power, then now I get the same result by taking a value of function g, putting x and y, right? Here, if putting dot does not makes a problem even if you put a single number like 1, 1. So simply a value 1 is considered as 1 by 1 matrix. So you can think about it as an entry. You can put this dot operation in a 1 by 1 matrix. So there's no problem. So in many cases you're asked to put the dots in every formula of the function. So please be careful when you define your function. Most of the case, you have to put the dot, except for the plus and minus. You have to put the dot in front of multiplication and division and the power symbol. So we're going to use the script function later when we are going to write a program using MATLAB. So for now, let's recall what we learned in the lecture. We talked about the limit. So we have a limit of 1 plus 1 over n to the power n, as n goes from 1 to infinitely large integer. So we want to check that this limit check that the limit of this sequence exists and equal to E. Okay, so how do we check that the limit exists? So there's no way you can rigorously prove that this limit exists using MATLAB. MATLAB only computes analytically. So we're going to use large number of n, and if the value converges to some finite value, then we can guess that this limit exists. So let's use series of integers. Okay, so I want to define a series of sequence of integers from 1 to 100. I think that's enough for checking that limit exists. So how do we create an integer from 1, 2, 3, 4 and up to 100? The worst method is just defining this way. So you put 100 numbers here. Right? So you're not expected to do this. So instead of putting all these integers, you can simply put one what is called colon, right? It's a colon, 1 colon 100. Then let's see what happens. So we have another variable in the workspace, so we called n, which because we define n as at 1 to the 100, and its value is defined as 1 by 100 matrix in double format, right? Size is 1 by 100 and class is double. So if you double click it, it has 1, 2, 3, 4 and up to 100, right? So you can create an array of number using simply a colon symbol here. Another way of creating an array, more 카메라는 꺼졌는데 소리는 나오죠? 나올 거예요. 네. 이게 카메라가 열받아서 또 꺼졌어요. 좀 재미는 없겠지만 일단 카메라 없이 일단 합시다. So another way of creating an array is that you can put a step size of array. So if you plug in like 1 colon 2 colon 100, what it does is you start from 1, the first value indicates the start value, and 2 in the middle value indicates the step size. You skip 1 from 2 steps, and then you go from 1 to 3, 5, 7. So after you run this script, you get n, it now becomes 1 by 50 double matrix. So if you're looking at this value by double click it, then you get 1, 3, 5, 7 and up to 99. Why 99? Although we set the n value of 100, but because the step size is 2, after you reach to 99, the next value is 101, which exceeds the n value 100. So you only goes up to 99, which is less than 100. So you can use you can change the step size here, and so this is different from creating a array using linspace. So linspace, as we explained in the previous lecture, we have 1 to 100, right? And let's compare the difference between n and m here. So m creates 1, 2, 3, 4 and up to 100, total 100 value of array, right? Now, it seems like linspace cannot be used when you want your step size or size of a matrix. There's another option that you can use in the linspace. You can set how large this your array should be. So basically, if you indicates the first value, the start value, and end value, it only creates the array of size 100. So only creates the array of 100 elements. But if you want 50 elements instead of 100 elements, you just put another options here like 50, and that indicates that create an array start from 1 to 100 with 50 numbers. Okay. So now you can expect that this 50 means that, oh, because I'm going to use I'm going to create a 50 size, a 1 by 50 matrix of array. You can expect this n created by colon and m created by linspace are the same. You may expect these two the variables to be the same, but you see that these two arrays are not the same. The n created by colon consists of integers 1, 3, 5. But however, m does not consist of integers, right? 1, almost 3, but not exactly 3, right? But consider, look carefully when m ends. M ends at 100 instead of 99 in the case of n. So in the n case, we have array ended up at 99, but m ended up at 100. So the difference between defining array using colon and linspace is that colon strictly follows the step size too. So it doesn't follows the 100 here. So 100 is just indicating that your value in the array cannot exceed this much. But in M, in the linspace, it satisfies the entire these options. So we have first value and n values, and you're going to divide your interval from 1 to 100 into 50 number of values. So 50 includes the first and the last values. So including the first and the last, divide this 1 to 100 equally into the array. So what happens? I mean, what you have to do in order to create the same array as n is that you have to put 99 here. Then you get the same array as n. Or if you still want your n value to be 100, then you have to how much number you have to need. I think it's impossible to create 135 using 100 here. So in order to create, let's say, what's the good value? I think there's no integer step size value, right? 1 from 1 to 100. So anyway, it's a 50. So there's no way you can create an integer step size value of array using the linspace. So in this example, you're going to use the integer only, so not going to use the linspace here. And then let's create the sequence. How do you create a sequence? So sequence, say A, array is defined as 1 plus 1. Can I use divide by n to the power of n? Now this makes a problem because you cannot divide 1, the real number, by 1 by 100. So let's just use a 1 by 100 array here. 1 by 100 array. You can divide two equal size square matrix to get two equal-sized square matrix. You can divide two equal-sized square matrix, but you cannot divide the different size matrix. So, and also that's not what we want. We want the reciprocal 1 over n of each entry of n, right? So you put the dot here. And also you want the power of each entry of n in the entire matrix power. So this is what we want. And then I'm putting semicolon after all these command line because I don't want the entire outputs to be shown because I just need the end. Because you see, what is A1? That's the so that's 2, right? So how do we get the A1 equals 2? Because the first value of n is 1, and I plug in the 1 in the place of n here, so you get 1 plus 1 to the power of 1, that's 2, right? What about A2? That's 2.25. That's given by 1 plus 1 over 2 to the power of 2. So basically 3 over 2 to the power of 2. So that's 2.25, and so on. So if you keep finding what happens to the value of the array, that's the value of sequence of 1 plus 1 over n to the power of n. And let's see what happens at the end. Because A is total of 1 by 100 double matrix. So the value almost looks like 2.7048. And let's compare with the exponential natural constant. Okay, so it's a little bit long way to go. The value runs up to 2.71, but when you compute the n equals to 100, then it's still not exactly the same natural number. And then let's increase the amount. So you can choose your n as 1 to 1000 integer array of 1000 elements, but also you can put the step size, because if you don't want the entire 1 to 1000, we only want to check the last one, so you can use this one. Okay, 100. So now I use the step size 10 from 1 to 1000. So basically you have 1 times 100 size of matrix n. So when you want to compute the integer 1000 for this sequence, so basically if you want to compute 1 plus 1 over 1000 to the power of 1000, then you have to call the end value of the array A, which is 100 position, the 100th position of the array A. Then now it's almost equal, so almost equal. Okay, so you see the value is getting close to the actual number of the natural number. And let's try to compute. Let's try to plot these values. So let's plot the points. So the x value, the horizontal line, is the array of n. So here we have step size 10 from 1 to 1000, and then the y value is the value of a, the sequence. So we have a. So if you plot this way, you get a series of lines connecting the points from n to a, right? So plotting the lines connecting the point whose x coordinates from n and y coordinates from a. But instead, I want to plot the point, not the line connecting points. So you can put dot. So this is another option when you plot a graph. So if you don't want the lines, if you don't want the line, but you want the point to be plotted, then you put the dot here. And somehow you want to increase the size of your marker, the point marker, then you can increase the size of marker size. using this option. Basically, default is 1, so I'm increasing twice. See what happens. Okay, so this is the result. So you start from, can you see it clearly? Maybe you cannot see clearly, but start from almost equal to 2.6, but now it increases and then stabilizes at some point. You can see a slightly increase at each point to 2.7 something. And then if you keep doing this, you can expect that this sequence will not diverge at some point, because you see the trends of these points is getting to converge to some point near 2.7, and that's how you check the limit exists. Okay, and then let's plot some other graphs here. So we have x times sine 1 over x. So this is a comment. So I'm not following the MATLAB syntax. So let's plot this function. Okay, so let's say we start from linspace from -5 to 5, and y as x times sine 1 minus x. Okay. I think this could make a problem because x contains 0. If x contains 0, if this array defined as a linspace from -5 to 5 consists of 100 elements contains 0, then there is an error message coming from this formula. If it's not, then it's okay, but let's see what happens. Okay, I think there's no error message, so let's plot this. Okay, so you see, this is not really accurate because we have -5 to 5, and then here, in order to have lots of oscillation here, we need to have more points near 0, but we only have 100, so there's not enough point to not enough points to plot the infinite oscillation near 0. So let's decrease the interval from -1 to 1 and then increase the number of points in this array. Let's say 1000 instead of 100. So default is 100. And then you see, oh, okay, so now it makes more sense. Now there are more sequence, more oscillation here. If you keep enlarge this, okay, a little bit lagging here. So if you can enlarge the point near 0, 0. Okay, here's 0. Okay, now it's working. So if you keep enlarging it, you see there's a little bit smooth. It looks smooth at the bigger picture, but now it becomes sharpened. So basically what this plot does is just connecting all the dots, connecting dots with lines. So we have very sharp points here, just connecting dots. So maybe in the real graph, it may not be that sharp, or it may not be that low or high, but it's just an indication how this looks like approximately. So if you put more points near 0, or you can just put more smaller domain, then now you can also see that these asymptotic lines that almost follow y equals to x. Now let's compare this graph with the graph that we considered when we're talking about the differentiability. So I used the 10,000 points from minus 0.1 to 0.1. Now, if you're looking at this function, we emphasize that this function is differentiable at 0. And the previous one is not differentiable at 0. So I a little bit exaggerated when I... Yeah, 3 or more dimensional array. MATLAB makes... Yeah, you can create any dimensional array. Let me explain later. So this one has a differentiability at 0, and you can see that the slope, there's no slope here. If you enlarge this, it still oscillate, but intuitively it looks like almost flat at 0. So that's why this function is differentiable. So you can consider the differentiability of a function as something like the function is flattened out, or you can measure the slope approximately. Okay, so there's also a question about how to create higher dimensional array. So you can define your two-dimensional array as A equals to 1, 2, and 3, 4 up, and you can put a column here, or may not be the column here. If you want higher dimension, usually if you want the higher dimension for non-intuitive situation, so let me teach you another command that you can create an array with a command. So ones is a command that creates the matrix of entry 1. So it consists of ones in the entire array. So suppose that you have ones 1, 100. You create 1 by 100 array of ones. So all the entries are 1. So you see all the ones are here. So now what happens when I put another one? So 1 means number of row and 100 means the number of column. What happens when I put another size here? So instead of output, let's just look at the workspace. So my variable A is now 1 by 100 by 100 double. So this is 3-dimensional array. Okay. So although this is always 1, so let's say A1. I'm sorry. So A 1, 1, 1. So this is 1. So I'm calling first. So there's no row and column. So first dimension index is 1. Second dimension index 1. Third dimension index 1. The entry of that is 1. So that's how we define multi-dimensional array. If you want to store entire data into one symbol or one variable, this multi-dimensional array is very useful. Or you can define an array of matrix or array of array. Then this the multi-dimensional array comes naturally. Or you can define an array of zeros. 5, 5, 5, 5, 5, 5, 5, 5, and so on. You can put any dimension here. So basically, when you run this, you get 3-dimensional array for A, 5-dimensional array for B. Okay. Here we have 5-dimensional double. Okay. Any other questions? Right. Index does not start from 0. I think it's, if you're familiar with Python, yes, it always starts from 1. That's very important. Sometimes very confusing because when your index start from 0, it's very convenient when you write a for iteration. But MATLAB start from 1, always index start from 1. Okay. So there are lots of functions. There are lots of functionality of MATLAB. You can not only just write your comment, but also you can compute symbolically some formula. For example, you can take a derivative, or you can take an integration in symbol. So this is the side note. It's almost over. So let's say define a and or let's say here we have x here, sim x. So basically MATLAB variable only contains the values or array of values, but I can define my variable as symbolic